So here's something you probably haven't thought about in a while. Right now, wherever you are, your body is radiating heat. Not a little bit, a lot. You're putting out roughly the same amount of energy as a 100-watt light bulb, just lying there, just breathing, just being alive. That warmth is streaming off your skin in invisible infrared radiation, drifting into the air, spreading into the walls and the ceiling and the blankets around you. And the blankets aren't actually making you warm. That's a common misunderstanding. The blankets have no heat of their own. They're just slowing down the rate at which your body's heat escapes into the cooler air. They're trapping the warmth you're already producing, the warmth that comes from the chemical reactions happening inside your cells right now. Billions and billions of tiny molecular engines converting the food you ate today into energy and releasing heat as a byproduct. You are, in the most literal sense, a heat engine, a soft, complicated, deeply improbable heat engine lying in the dark. And heat, what it is, where it goes, why it flows the way it does, what you can and can't do with it. That's the story we're going to tell tonight. The story of thermodynamics. Which sounds like a dry, technical word, and honestly, it kind of is. It comes from the Greek, therme for heat, dynamis for power, the power of heat. But behind that dry word is one of the grandest, most dramatic, most consequential stories in all of science. It's a story about fire and engines and the Industrial Revolution, about fortunes made and lives lost, about a young French soldier who figured out the deepest truth about engines and then died before anyone understood what he'd done, about a brewer's son who spent years stirring water with paddles to prove a point everyone thought was obvious, about a brilliant, tormented Austrian physicist who took his own life because the scientific establishment refused to believe that atoms were real, and then was proved right almost immediately after he died. Thermodynamics is the science of heat and energy, and the rules that govern how they move and change. And here's the thing, these rules are not optional. They're not suggestions. They're not like traffic laws that sometimes get broken. The laws of thermodynamics are the most ironclad, most universally obeyed rules in all of physics. Nothing violates them. Not atoms, not stars, not galaxies, not black holes. Einstein once said that thermodynamics is the only physical theory of universal content that, within the framework of its basic concepts, will never be overthrown. That's a strong statement from a man who overthrew quite a lot of physics himself, and he was right. More than a century later, the laws of thermodynamics have survived every challenge, every test, every attempt to find an exception. They stand. So let's start at the beginning. And the beginning, really, is fire. Humans have been using fire for at least 1 million years, maybe longer. Long before we had language, long before we had agriculture or cities or writing, we had fire. We cooked with it, warmed ourselves by it, used it to harden tools, to clear land, to frighten predators. Fire was the first technology, the first way humans bent the physical world to serve their needs. And for most of that 1 million years, nobody had the faintest idea what fire actually was. Think about how mysterious it must have seemed. You take a piece of wood, something solid and heavy, and you set it alight, and it transforms. It gives off heat and light, enormous amounts of both, and when it's done, almost nothing is left. Just a handful of ash. Where did the rest of it go? Where did all that heat and light come from? What is fire? Is it a substance, a spirit, a process? For thousands of years, the best anyone could offer were stories and speculation. The ancient Greeks had their element of fire, one of the four fundamental building blocks of the universe, alongside earth, water, and air. Heraclitus, around 500 BCE, thought fire was the most fundamental element of all, the primordial substance from which everything else derived. But that was philosophy, not science. Nobody could actually explain the mechanism, and it stayed that way for a remarkably long time. There were interesting detours along the way. In the 18th century, the German chemist Georg Ernst Stahl proposed a substance called phlogiston that was supposedly released during combustion. Things that burned well, like wood and charcoal, were supposedly rich in phlogiston, and burning released it into the air. When the air became saturated with phlogiston, the fire went out. It was clever, and it explained some observations. But it was also completely wrong. Lavoisier demolished the phlogiston theory in the 1770s and 1780s by showing that combustion was actually a chemical reaction with oxygen, that when things burned, they combined with oxygen from the air rather than releasing some mysterious substance. That was a huge advance for chemistry. But the nature of heat itself remained murky. Even into the 1700s, the dominant theory of heat, the one taught in universities, the one serious scientists believed, was something called the caloric theory. And it's worth spending a minute on this, because understanding how wrong it was helps you appreciate how hard-won the right answers turned out to be. The caloric theory said that heat was a substance, an actual, physical, weightless fluid called caloric that permeated all matter. When something was hot, it contained a lot of caloric. When it cooled down, the caloric flowed out of it into whatever cooler thing was nearby. That's why a hot poker cools down when you put it in water. The caloric is flowing from the poker into the water, like water flowing from a higher container to a lower one. It was elegant, intuitive, and it explained a lot of everyday observations quite nicely. Antoine Lavoisier, the great French chemist, the man who essentially invented modern chemistry, was a strong proponent of caloric theory. He even listed caloric as one of the elements in his table. That's how seriously it was taken. And you can see why it was appealing. Heat really does seem to flow, doesn't it? You put your hand on a cold railing and the heat flows out of your hand. You drop an ice cube in a warm drink and the heat flows into the ice. It's natural to think of heat as a stuff, a fluid that moves from hot things to cold things. The caloric theory even explained some fairly subtle phenomena, like why gases expand when heated. The caloric particles were supposed to repel each other, so when you added more caloric to a gas, the particles pushed apart and the gas expanded. But there were problems. And the most dramatic early challenge came from a person you might not expect, an American-born adventurer, spy, social climber, and occasional scientist named Benjamin Thompson, better known as Count Rumford. And his story is genuinely wild. Thompson was born in 1753 in Woburn, Massachusetts. He was clever, ambitious, and not terribly burdened by loyalty. During the American Revolution, he spied for the British. When that became inconvenient, he fled to England. When England got boring, he moved to Bavaria, where he somehow became a count of the Holy Roman Empire, hence the name Rumford. He reorganized the Bavarian army, improved their cannons, invented a more efficient fireplace, and in his spare time conducted a series of experiments that would help overturn the caloric theory. The experiment that matters most for us happened in 1798 at the military arsenal in Munich. Rumford was overseeing the boring of cannons, drilling out the barrel of a brass cannon using a large boring tool, and he noticed something that bothered him. The process generated enormous amounts of heat. Enormous. The brass shavings were scalding hot. You could boil water with the heat produced by boring a cannon. And here's what struck him. The heat kept coming. As long as you kept the boring tool turning, heat kept pouring out. If heat were a substance, a fluid contained in the brass, then eventually you'd run out. You'd extract all the caloric from the metal, and no more heat would appear. But that's not what happened. The heat was inexhaustible. As long as mechanical work was being done, as long as the horses kept turning the boring bar, heat kept flowing. Rumford concluded that heat could not be a substance. It had to be a form of motion. The mechanical work of the boring tool was being converted into heat, into the jiggling and vibrating of the tiny particles that made up the brass. He published his results and his conclusions, and they were largely ignored, or at least not taken as seriously as they deserved to be. The caloric theory was too well established, too useful, too deeply embedded in the way physicists and chemists thought about the world. It would take another 50 years and a lot more evidence before it finally fell. But Rumford had planted a seed, and that seed, the idea that heat and mechanical work are somehow interchangeable, that one can be converted into the other, that's the idea that would eventually grow into thermodynamics, and the soil in which it grew was not some abstract philosophical garden. It was the gritty, coal-smeared, steam-driven reality of the Industrial Revolution. Because thermodynamics didn't begin as a pure science. It began as an engineering problem, maybe the most important engineering problem of the 18th and 19th centuries. How do you get useful work out of heat? And to understand that problem, we need to talk about steam engines, which means we need to talk about a specific problem that had been plaguing England for over a century: flooded mines. See, by the late 1600s, England was running on coal. Coal heated homes, powered industries, and was a major export. But the easy coal, the stuff near the surface, was running out. Miners had to dig deeper, and the deeper they dug, the more water they encountered. Groundwater would seep into the shafts, flooding them, making them unworkable. Pumping that water out by hand, or with horse-driven pumps, was slow, expensive, and couldn't keep up with the deeper mines. What they needed was a machine that could pump water tirelessly, powered by something cheap and abundant. And what was cheap and abundant at a coal mine? Coal. The first practical answer came from Thomas Newcomen, an ironmonger from Dartmouth in Devon. Newcomen wasn't a scientist. He wasn't a university-trained natural philosopher. He was a hardware dealer who sold tools to the mining industry and understood their problems intimately. And around 1712, after years of tinkering, he built something remarkable: the first commercially successful steam engine. Now, calling Newcomen's machine a steam engine is technically correct, but it might give you the wrong picture. It wasn't like a locomotive. It was enormous, it was slow, and it was stunningly inefficient. But it worked. And here's how. You had a large vertical cylinder with a piston inside. Steam from a boiler filled the cylinder, pushing the piston up. Then, and this is the clever bit, you sprayed cold water directly into the cylinder, which condensed the steam back into water. Now, liquid water takes up vastly less space than steam, roughly 1,700 times less. So when the steam condensed, it created a partial vacuum inside the cylinder, and atmospheric pressure, the weight of the air above, pushed the piston back down. It wasn't really the steam pushing the piston, it was the atmosphere. The steam just created the conditions for atmospheric pressure to do the work. That's why it's more properly called an atmospheric engine. The downward stroke of the piston was connected by a big rocking beam to a pump rod that went down into the mine, and each stroke pulled water up, back and forth, up and down, day and night. Newcomen's engines spread across the mining districts of England. They were big, they were loud, they burned prodigious amounts of coal, and they were terribly wasteful. Maybe 1% of the energy in the coal actually ended up as useful pumping work. But when you're sitting on top of a coal mine, fuel is basically free, so nobody cared much about efficiency. The engines did their job. They kept the mines from flooding, and for about 50 years that was good enough, until a young instrument maker at the University of Glasgow picked up a model Newcomen engine that needed repairs, and in fixing it, saw something that would change the world. His name was James Watt, and the year was 1764, and what happened next is one of the great stories in the history of engineering. Watt was born in 1736 in Greenock, Scotland, a port town on the Firth of Clyde. His father was a shipwright and merchant, his mother was well educated, and the young Watt was sickly, shy, and extraordinarily good with his hands. He became a mathematical instrument maker, the person who built and repaired the precision tools that scientists used, and the University of Glasgow gave him a small workshop on campus. It was there that a professor named John Anderson brought him a model of a Newcomen engine that wasn't working properly. It was a teaching model, a small-scale replica used in lectures on natural philosophy, and it kept running out of steam after a few strokes. Watt started tinkering with it, and as he did, he began to understand just how wasteful the Newcomen design really was. The fundamental problem was this: every cycle, you heated the cylinder with steam, then cooled it with cold water to condense the steam, then heated it again with more steam. You were alternately heating and cooling the same metal cylinder, over and over and over. And every time you injected cold water, you didn't just condense the steam, you also cooled the cylinder walls. So the next batch of steam that entered had to spend a huge fraction of its energy just reheating the cylinder before it could even fill the space and push the piston. Most of the energy was being wasted on this endless cycle of heating and cooling the same piece of metal. Watt saw the problem clearly. The cylinder needed to stay hot all the time, but the steam also needed to be condensed. How could you do both? And the answer came to him, according to the famous story, on a Sunday afternoon walk across Glasgow Green in the spring of 1765. What if you condensed the steam somewhere else? What if you kept the main cylinder hot and connected it, through a valve, to a separate, cool vessel, a separate condenser, where the steam would rush over and condense? That way, the cylinder would never have to be cooled. It would stay hot, and you could condense the steam in a dedicated chamber that was kept cold. Hot stays hot. Cold stays cold. No more wasting energy on that miserable cycle of heating and cooling the same cylinder. It was a beautiful insight, elegant, practical, and once you hear it, almost obvious, which is usually the sign of a truly great idea. And here's a lovely detail that connects to a deeper piece of the thermodynamics story. The reason Watt understood the problem so clearly was partly because he'd been talking to Joseph Black, a professor of chemistry at the University of Glasgow and one of the most important early investigators of heat. Black had discovered something crucial, the concept of latent heat. He'd shown that when ice melts or water boils, it absorbs a tremendous amount of heat without its temperature changing at all. You can keep pumping heat into a pot of boiling water, and the temperature stays stubbornly fixed at 100 degrees Celsius. All that energy goes into changing the state of the water, from liquid to gas, not into raising its temperature. Black called this hidden heat latent heat, from the Latin for hidden, and it explained why steam carries so much energy. A kilogram of steam at 100 degrees contains enormously more energy than a kilogram of liquid water at 100 degrees, because of all the latent heat that went into converting the water to steam. Watt understood this, and it helped him see exactly how much energy was being wasted in Newcomen's cycle. Every time cold water was sprayed into the cylinder to condense the steam, all that latent heat, that enormous investment of energy that had gone into creating the steam in the first place, was being thrown away. The cylinder walls absorbed some of it, the condensed water carried the rest down the drain, and the next cycle had to start over from scratch. The separate condenser solved this by keeping the energy where it belonged. But getting from the insight to a working engine took Watt years of painstaking development, desperate fundraising, and a partnership with the Birmingham industrialist Matthew Boulton that would eventually make both men rich and transform the face of the world. By the 1770s and 1780s, Watt's improved engines were spreading across Britain, and they were dramatically more efficient than Newcomen's. Where a Newcomen engine converted maybe 1% of the coal's energy into useful work, Watt's engines could manage 3 or 4%, which doesn't sound like much in absolute terms, but it meant using 1/3 or 1/4 as much coal for the same work. Suddenly, steam engines were economical even where coal wasn't free. They could be used in factories, in mills, in breweries, anywhere you needed power, and that changed everything. But here's what's interesting for our story. All of this, Newcomen, Watt, the separate condenser, the massive expansion of steam power across Britain, and then the world, all of this happened without anyone really understanding the fundamental science of what was going on. Engineers were building and improving these engines through intuition, trial and error, practical know-how. They knew that burning coal made steam, and steam could push pistons, and pistons could do work. But the deep question, the theoretical question of how heat becomes work, what the fundamental limits are, whether there's some ultimate efficiency that no engine can exceed, nobody had asked that yet. Nobody had tried to build a science of heat engines. It was all craft and no theory. And that's about to change, because in Paris, a young man from a very famous family is about to ask exactly the right question. His name is Sadi Carnot, and he's the son of Lazare Carnot, one of the most powerful men in revolutionary and Napoleonic France, a mathematician, military strategist, and politician who was known as the organizer of victory for his role in mobilizing the French armies during the Revolutionary Wars. Sadi was named after a medieval Persian poet, which gives you a sense of the family's intellectual range. He was born in 1796, trained as a military engineer at the prestigious École Polytechnique, and by his mid-20s, he was turning his attention to a question that obsessed him. Why were the British so far ahead in steam engine technology? And more importantly, was there some fundamental theoretical limit to how good a steam engine could get? The question mattered to Carnot for patriotic reasons. France was falling behind Britain industrially, and steam power was the key technology of the age. But it also mattered to him intellectually, because he sensed that there was a deep principle hiding inside the practical problem. And he was right. The answer he found would become the foundation of the entire science of thermodynamics, and it would come in the form of a slim, elegant book published in 1824, when Carnot was just 28 years old. The book was called Reflections on the Motive Power of Fire, and almost nobody read it. Carnot's starting point was a simple analogy. Think about a water wheel. A water wheel produces work. It turns, it grinds grain, it drives machinery, because water falls from a higher level to a lower level. The water at the top has gravitational potential energy, and as it falls, that energy is converted into the mechanical motion of the wheel. The amount of work you can get depends on two things: how much water there is and how far it falls. A trickle falling a great height can do as much work as a torrent falling a small distance. And here's the key. The water isn't used up. It's still there at the bottom, just at a lower level. The water is a carrier of energy, not a source of it. The energy comes from gravity, from the height difference. Carnot proposed that heat engines work the same way. Heat, he said, flows from a hot source to a cold sink, like water falling from a height. And as it flows, you can extract work from it, just as a water wheel extracts work from falling water. The hot source is like the reservoir at the top. The cold sink is like the pond at the bottom. And the amount of work you can extract depends on the temperature difference between them, the thermal height the heat falls through. Now, Carnot was actually still using the caloric theory when he wrote this. He thought of heat as a substance flowing from hot to cold, just like water flowing downhill. And in one important sense, he was wrong about that. Heat isn't a substance, as Rumford had suspected and as later scientists would prove conclusively. But here's the remarkable thing. Even though Carnot's underlying model of heat was wrong, his conclusions about engine efficiency were exactly right. They survived the death of the caloric theory completely intact. That almost never happens in science, and it's a testament to the depth and clarity of Carnot's thinking that his results were robust enough to outlast the framework he built them in. So what did Carnot actually prove? He imagined an idealized engine, a perfect, frictionless engine operating in a specific cycle that we now call the Carnot cycle. And he showed that this ideal engine sets an absolute upper limit on the efficiency of any heat engine operating between the same two temperatures. No real engine can ever be more efficient than a Carnot engine, not because of engineering limitations, not because of friction or heat leaks or imperfect materials, but because of the fundamental nature of heat and work. It's a theoretical ceiling that no amount of cleverness can break through. And the efficiency of a Carnot engine depends on only one thing: the ratio of the temperatures of the hot source and the cold sink, measured on an absolute scale. The bigger the temperature difference, the higher the maximum possible efficiency. If your hot source is at 1,000 degrees and your cold sink is at 500 degrees, measured in absolute terms, then the best you can possibly do is 50% efficiency. Half the heat becomes work, and the other half has to be dumped into the cold sink. You can never, ever turn all the heat into work. Some of it must always be discarded. That's not a limitation of our engineering. It's a law of nature. Think about what that means for a second. It means that every power plant, every car engine, every jet turbine in the world is fundamentally, inescapably limited in how much of the fuel's energy it can convert into useful work. A modern coal-fired power plant operates at maybe 33 to 40% efficiency. The best combined cycle gas turbines can push past 60%, but nobody will ever build a heat engine that converts 100% of heat into work. Carnot proved that in 1824, and 2 centuries of engineering have confirmed it absolutely. And then Sadi Carnot died in 1832, at the age of 36, during a cholera epidemic in Paris. Most of his papers and belongings were burned, as was the custom with the possessions of cholera victims, to prevent the spread of the disease. His little book, Reflections on the Motive Power of Fire, had sold almost no copies. He had published no other major works. The most important insight in the history of heat science was sitting in a handful of libraries, unread and unappreciated, written by a dead man whose papers had been destroyed. It's one of those moments in the history of science that just aches. Carnot had seen further than anyone into the fundamental nature of heat and work, and then he was gone, and the world barely noticed. If his work had been lost entirely, and it very nearly was, the history of thermodynamics would have unfolded very differently, but it wasn't lost. In 1834, a French engineer and physicist named Émile Clapeyron read Carnot's book and recognized its importance. Clapeyron took Carnot's sometimes verbal, sometimes intuitive arguments and recast them in precise mathematical language, with equations and diagrams. He published a paper summarizing and extending Carnot's ideas, and it was Clapeyron's paper, not Carnot's original book, that eventually reached the two men who would build the full science of thermodynamics, Rudolf Clausius in Germany and William Thomson in Britain. But that was still years away. The ideas needed time to percolate. Meanwhile, in a brewery in Manchester, a quiet, meticulous, deeply stubborn young man was conducting a series of experiments that would answer a different but equally fundamental question. What exactly is the relationship between heat and mechanical work? His name was James Prescott Joule, and the fact that he came from a brewing family turns out to be important, because brewers knew a lot about temperature. Their livelihood depended on controlling heat precisely. Too hot and you kill the yeast, too cold and fermentation stalls. Joule grew up surrounded by thermometers and a culture of precise measurement, and he brought that precision to his physics. Joule's great contribution was establishing the mechanical equivalent of heat, proving, through careful and repeated experiments, that a specific amount of mechanical work always produces a specific amount of heat, and vice versa. The most famous version of his experiment, the one you see in every physics textbook, involved a falling weight connected by a string over a pulley to a set of paddles inside an insulated container of water. As the weight fell, the paddles turned, stirring the water. The stirring heated the water, and Joule measured the temperature rise with painstaking care. He also measured exactly how far the weight had fallen, which told him exactly how much mechanical work had been done, and the ratio, the amount of work needed to produce a given amount of heat, was always the same, always. Regardless of how the work was done, you could stir water, compress air, rub metal surfaces together. It didn't matter. The conversion factor was constant. This was huge. It meant that heat and mechanical work were interchangeable forms of the same thing, energy. Heat wasn't a substance, not a fluid called caloric. It was a form of energy, and it could be converted into other forms of energy and back again, at a fixed exchange rate. Rumford had suspected this 50 years earlier, but Joule proved it, with numbers, with precision, with the kind of careful experimental work that leaves no room for doubt. Joule first presented his results in 1843, and the response was underwhelming. He was young, he was from Manchester, not exactly the center of the scientific universe, he wasn't affiliated with a prestigious university, and his results challenged the caloric theory that most physicists still accepted. When he presented at a meeting of the British Association for the Advancement of Science in 1847, the chairman was about to move on without discussion when a young man in the audience stood up and asked some penetrating questions. That young man was William Thomson, not yet Lord Kelvin, just 23 years old, and already recognized as one of the most brilliant mathematical physicists in Britain. Thomson was immediately fascinated by Joule's work, because he could see what it meant for the theoretical framework he was trying to build. The two men became close collaborators and lifelong friends, despite their very different styles. Joule, the meticulous experimenter, Thomson, the soaring theorist. Together, they would discover the Joule-Thomson effect, which describes how gases cool when they expand through a valve, a phenomenon that turns out to be essential for liquefying gases and for the whole science of cryogenics. That encounter, the careful brewer's son from Manchester, and the precocious young professor from Glasgow, meeting over a contested presentation at a scientific conference, would prove to be one of the most consequential meetings in the history of physics. But that's getting ahead of ourselves a little. The point, for now, is this. By the late 1840s, the pieces were falling into place. Carnot had shown that there are fundamental limits to what heat engines can do. Joule had shown that heat and work are interchangeable forms of energy. And these two insights were about to be unified into something much bigger: the first and second laws of thermodynamics. The first law is essentially Joule's insight, stated as a universal principle. Energy can be converted from one form to another, but it cannot be created or destroyed. The total energy of a closed system is always conserved. You can turn heat into work, or work into heat, or kinetic energy into potential energy and back. But the books always balance. Nothing comes from nothing. You can't get something for free. That sounds almost obvious, doesn't it? Almost trivially true. But it took decades of argument and experiment to establish, because it required letting go of the caloric theory, which had served scientists well for a long time, and stating it precisely, in a way that could be applied to any system, required a level of mathematical rigor that the early pioneers hadn't quite achieved. The person who first stated the first law with full generality was a German physician and physicist named Hermann von Helmholtz, in a landmark paper published in 1847, though the idea was also developed independently by Julius Robert von Mayer, a German physician who had his own fascinating story involving the color of blood in the tropics. Mayer noticed that the venous blood of sailors in the Dutch East Indies was redder than he expected, closer to arterial blood, and he reasoned that this was because their bodies needed to burn less fuel to maintain body temperature in the tropical heat, so less oxygen was being extracted from the blood. From this observation, he leapt to the conclusion that the body's heat and its mechanical work both come from the same source, the chemical energy in food, and that the total energy is conserved. It was a brilliant, intuitive leap, though Mayer was not a strong enough mathematician to formalize it properly, and he received little credit during his lifetime, which drove him to a nervous breakdown and a suicide attempt. The history of thermodynamics is full of these tragedies. Brilliant people who see the truth before anyone else and suffer for it. But the first law, however important, is really just the beginning. It tells you that energy is conserved, that the books balance, that you can't create or destroy energy. But it doesn't tell you which way things go. It doesn't explain why heat flows from hot to cold and never the other way. It doesn't explain why your coffee cools down, but never spontaneously heats up by absorbing warmth from the cooler air. The first law would be perfectly happy with either direction. Energy would be conserved if your cold coffee suddenly got hotter and the air got colder. The math works both ways, but it never happens. Something else is going on, something the first law doesn't capture, and understanding that something, that deeper, more subtle principle, is where thermodynamics gets really interesting. It's where we meet the second law, and it starts with Rudolf Clausius, and a concept so profound, so far-reaching, that it touches everything from the efficiency of engines to the fate of the universe itself. And that concept has a name that Clausius himself invented, a word he deliberately made up from Greek roots to sound like energy, because he felt the two ideas were closely related. The word is entropy, and it's one of those words that gets thrown around a lot, often loosely, often incorrectly, but when you really understand what it means, it changes the way you see the world. Rudolf Clausius was born in 1822 in Koslin, Prussia. That's in present-day Poland, the son of a pastor and school principal. He studied physics and mathematics at the University of Berlin, and he had a gift for taking messy, intuitive ideas and sharpening them into precise mathematical statements. That's exactly what thermodynamics needed at this point in its history. The experimental work had been done. The key observations were in. What was missing was the theoretical framework, the clean, rigorous, universal principles that tied everything together. And Clausius was the person who provided them. In 1850, Clausius published a paper that is often credited as the founding document of thermodynamics as a formal science. In it, he took Carnot's insights about heat engines and Joule's proof that heat and work are interconvertible, and he reconciled them. See, there was a tension between Carnot and Joule. Carnot's analysis, based on the caloric theory, assumed that heat is conserved, that the same amount of heat flows out the cold side of an engine as flows in the hot side, and the engine just extracts work from the flow. But Joule had shown that heat and work are interconvertible, which means some of the heat going into an engine actually gets converted into work and doesn't come out the cold side at all. So who was right? Clausius showed that Joule was right about the nature of heat. It's energy, not a substance. But Carnot was right about the limits on efficiency. You could have both. The first law says energy is conserved. The second law says something about the direction of that flow. It says that heat naturally flows from hot to cold, never the other way, and that this directionality puts fundamental limits on what you can do. Now, here's where it gets interesting. Clausius initially stated the second law in a very simple, almost homely way. Heat cannot, of itself, pass from a colder to a hotter body. That's it. Heat flows downhill. Hot things warm up cold things, not the other way around. Seems obvious, right? Almost too obvious to be a law of physics. But think carefully about what it's saying. It's not just saying that heat usually flows from hot to cold, or that it tends to flow that way, or that it flows that way most of the time. It's saying that a spontaneous transfer of heat from a cold object to a hot object is impossible. Period. It cannot happen on its own. You can make it happen. That's what a refrigerator does. It pumps heat from the cold inside to the warm kitchen. But it requires work. It requires energy input from somewhere else. Left to its own devices, heat only flows one way. And that one-wayness, that irreversibility, is the key to everything the second law tells us. William Thomson, working independently in Glasgow, arrived at a different but equivalent formulation of the same law. Thomson, who would later become Lord Kelvin, one of the most titled and honored scientists of the Victorian age, stated it this way: "It is impossible to extract heat from a single reservoir and convert it entirely into work without any other effect." In other words, you can't build an engine that simply absorbs heat and turns all of it into work. Some heat always has to be dumped into a cooler sink. Always. That's exactly what Carnot had found with his ideal engine. You need a hot source and a cold sink, and you can never convert all the heat into work. Thomson's statement and Clausius's statement look different on the surface, but they're logically equivalent. If you could violate one, you could violate the other. They're two faces of the same fundamental truth, and that's worth sitting with for a moment, because these two statements, heat flows from hot to cold, and you can't convert heat entirely into work, together rule out an enormous number of things that would otherwise seem perfectly possible. They rule out perpetual motion machines of the second kind, machines that run forever by converting heat from their surroundings into work. The ocean, for instance, contains a colossal amount of thermal energy. Couldn't you just build a ship that extracts heat from the seawater, converts it to mechanical work to turn the propellers, and sails around forever without burning any fuel? The first law doesn't forbid it. Energy would be conserved. The heat extracted from the water would exactly equal the work done by the propellers. But the second law says no, you can't do it, not because we haven't figured out how, but because the universe doesn't allow it. Now, Thomson made another contribution that turned out to be essential: the absolute temperature scale. See, Carnot's analysis of engine efficiency depended on the temperatures of the hot source and the cold sink, but temperature scales at the time were somewhat arbitrary. Celsius and Fahrenheit both pick their 0 points for practical reasons, the freezing point of water, for instance. But there's nothing physically fundamental about those choices. Thomson realized that Carnot's work implied the existence of a natural, absolute zero of temperature, a temperature at which all thermal motion ceases, a true rock bottom. And he proposed a temperature scale that starts at this absolute zero. We now call it the Kelvin scale, and absolute zero is 0 Kelvin, which corresponds to about -273 degrees Celsius, or -460 Fahrenheit. This is the coldest anything can possibly be. You can get close to it. Modern laboratories can cool atoms to billionths of a degree above absolute zero, but you can never quite reach it. That turns out to be its own law, the third law, and we'll get to that later. For now, the important thing is that with the Kelvin scale, Carnot's efficiency formula becomes clean and beautiful. The maximum efficiency of a heat engine operating between a hot source at temperature T hot and a cold sink at temperature T cold is 1 minus T cold divided by T hot, with both temperatures measured in Kelvin. Simple, elegant, and merciless. Here's a practical example. A typical coal-fired power plant might operate with steam at around 800 Kelvin going in and cooling water at around 300 Kelvin going out. Plug those numbers into Carnot's formula. 1 minus 300 over 800 equals 0.625, or about 63%. That's the absolute maximum efficiency. In practice, friction, heat losses, and imperfect processes reduce this further, and real coal plants typically achieve around 35 to 40%. Gas turbines, which operate at higher temperatures, can do better, especially in combined cycle plants where the waste heat from one turbine runs a second turbine. The best combined cycle plants push past 60% overall efficiency, which is getting impressively close to the Carnot limit for their operating temperatures. But the key insight remains: there is always waste heat, always. The second law demands it. But Clausius wasn't done. He kept refining his ideas throughout the 1850s and 1860s, searching for a deeper mathematical quantity that would capture this one-wayness of heat flow, this tendency of energy to spread and disperse. And in 1865, he found it. He introduced a new quantity, a mathematical function of the state of a system, and he called it entropy. He chose the word deliberately, from the Greek word trope, meaning transformation, and he chose it to sound like energy, because he felt the two concepts were deeply related, like siblings. So what is entropy, actually? This is one of those questions that sounds simple, but the deeper you dig, the more layers you find. At the level Clausius defined it, entropy is a measure of how much energy in a system is unavailable to do work. When you have a hot thing and a cold thing, there's a temperature difference, and you can extract work from that difference. That's what a heat engine does. But as heat flows from hot to cold, the temperature difference decreases, and the ability to extract work decreases. The energy isn't gone. The first law guarantees that. But it's more spread out, more evenly distributed, less concentrated, less useful. Entropy is a way of quantifying that spreading out. And here's the second law restated in terms of entropy, which is how Clausius ultimately expressed it, and it's the form that has the most reach. In any spontaneous process, the total entropy of the universe either stays the same or increases. It never decreases. Never. Not on its own. Think about what that means for a second. Every spontaneous process, every cup of coffee cooling, every ice cube melting, every fire burning, every star shining, increases the total entropy of the universe. The universe is a one-way street. Energy doesn't disappear, but it degrades. It spreads out. It goes from concentrated, useful forms to diffuse, less useful forms. Hot things cool down. Fast-moving things slow down. Differences even out. And this process is irreversible. You can locally decrease entropy. A refrigerator does it. A living organism does it. Anything that creates order from disorder does it, but only by increasing entropy somewhere else by an even larger amount. The total always goes up. Always. Clausius summarized the two laws of thermodynamics with beautiful economy. He wrote, "The energy of the universe is constant. The entropy of the universe tends to a maximum." 2 sentences. The entire foundation of thermodynamics. The first says, you can't win. You can never get more energy out than you put in. The second says, you can't even break even. Every real process wastes some energy, degrades some of it into less useful forms. Together, they paint a picture of a universe that is slowly, inexorably running down, spreading its energy thinner and thinner, its useful temperature differences smoothing out, its capacity for work diminishing. This idea, the eventual heat death of the universe, where entropy has reached its maximum and no more work can be done anywhere, became one of the most haunting concepts in all of science when Thomson and others worked out its implications in the 1850s and 1860s. The universe is winding down. Not quickly. It will take incomprehensible stretches of time, but inevitably. That's what the second law says. Now, I want to give you something concrete here, because entropy can feel abstract, and it's easier to understand when you see it working in real life. Think about a new deck of playing cards. Fresh out of the box, the cards are in perfect order, ace through king, suit by suit. That's a low entropy state. Now shuffle the deck. Shuffle it 7 times, which mathematicians will tell you is the minimum for a good randomization. Look at the cards. They're in some random order. A high entropy state. Now, here's the question. If you shuffle the deck again, is there any chance it will return to the original factory order? Technically, yes. It's not impossible. But the probability is 1 in about 8 times 10 to the 67th power. That's an 8, followed by 67 zeros. For all practical purposes, it will never happen. Not if you shuffled 1 billion times a second for the entire age of the universe. The low entropy state doesn't come back, not because it's forbidden by any law, but because there are so many more disordered arrangements than ordered ones, that randomness will essentially always take you toward disorder. Here's an everyday version of the same idea. Think about the air in your room right now. The oxygen and nitrogen molecules are spread roughly evenly throughout the space. That's the high entropy state. Uniform, well-mixed, boring. Now imagine all the air molecules spontaneously rushing to one corner of the room, leaving the rest in vacuum. There's nothing in the laws of mechanics that forbids this. Every individual molecular collision that would lead to this outcome is perfectly legal, perfectly consistent with Newton's laws. But the number of arrangements where the gas is evenly spread is so astronomically, incomprehensibly larger than the number of arrangements where it's bunched in a corner, that you could wait a trillion lifetimes of the universe, and it would still never happen. The high entropy state isn't mandatory. It's just overwhelmingly, crushingly more likely. And that, it turns out, is the deep secret of entropy. It's not really about heat or engines at all, ultimately. It's about probability. It's about the overwhelming statistical likelihood that things will move from less probable states to more probable states. And the person who saw this most clearly, who built the bridge between the macroscopic world of engines and temperatures and the microscopic world of atoms and statistics, was a man named Ludwig Boltzmann. And Boltzmann's story is one of the most brilliant and most heartbreaking in all of physics. Ludwig Boltzmann was born in 1844 in Vienna, during the Shrove Tuesday Ball, which he liked to joke was the reason for his wild swings of mood, born on the boundary between celebration and penitence. He was a big man, physically, stocky, energetic, with wild hair and thick glasses. He was also emotionally volatile, swinging between periods of intense productive energy and deep depression. He was, by most accounts, a passionate and generous teacher, the kind of professor who would get so excited about a mathematical derivation that he'd accidentally walk into furniture. And he had one great intellectual mission in life, to prove that the macroscopic properties of matter, temperature, pressure, entropy, could be explained by the statistical behavior of enormous numbers of atoms. Now, you might be thinking, well, of course, matter is made of atoms. Everybody knows that. But in Boltzmann's time, not everybody knew that. Or rather, not everybody believed it. In the late 19th century, the existence of atoms was still genuinely controversial. Yes, the atomic hypothesis had been useful in chemistry since John Dalton's work in the early 1800s. Yes, atoms explained a lot of chemical reactions and combining ratios. But a significant faction of physicists and philosophers, led by prominent figures like Ernst Mach and Wilhelm Ostwald, argued that atoms were just a useful fiction, a mathematical convenience, not real physical objects. They belonged to a school of thought called positivism, which held that science should only deal with things that can be directly observed and measured. And nobody had directly observed an atom. Nobody had seen one, touched one, weighed one individually. So why, they argued, should we pretend they exist? This might sound like a strange debate now, but at the time, it was deadly serious. Mach was enormously influential. Ostwald was a Nobel laureate. And Boltzmann, who believed atoms were real, who had built his entire life's work on treating gases as vast collections of atoms bouncing around, found himself increasingly isolated, increasingly under attack, increasingly exhausted by decades of bitter argument. But we're getting ahead of the story. Let me tell you what Boltzmann actually did, because it's extraordinary. Here's the problem Boltzmann was trying to solve. Clausius had defined entropy as a macroscopic quantity, a property of bulk matter that you measure with thermometers and pressure gauges. But what does entropy look like from the bottom up? If a gas is really just a huge number of atoms flying around, colliding, bouncing off walls, what microscopic property of all those atoms corresponds to entropy? What does entropy mean at the level of individual particles? Boltzmann's answer was both simple and profound. He said that entropy is a measure of the number of ways the atoms can be arranged. More specifically, it's related to the logarithm of the number of microscopic arrangements, the number of ways you could distribute positions and velocities among all the individual atoms that would produce the same macroscopic state, the same temperature, the same pressure, the same overall energy. He expressed this as a formula that is now carved on his tombstone in Vienna. S equals K log W. S is entropy. W is the number of microstates, the number of different microscopic properties you observe. And K is a constant, now called Boltzmann's constant, a tiny number that bridges the microscopic world of atoms to the macroscopic world of human-scale measurements. Let me unpack that with an analogy. Imagine you have a room with 10 coins, and you want to describe the overall state of those coins in terms of how many heads and how many tails you have. If all 10 are heads, there's exactly one way that can happen. Every single coin showing heads. That's W equals 1, and the entropy is very low. But if you have 5 heads and 5 tails, there are 252 different ways the individual coins can be arranged to give you that split. W equals 252. Higher entropy. And if you flip all 10 coins at random, you're overwhelmingly more likely to get something close to 5 and 5 than you are to get all heads or all tails. Not because the coins prefer disorder. They don't care. But because there are just so many more ways to be disordered than ordered. Now scale that up, way up. A single breath of air contains something like 10 to the 22nd power molecules, 25 sextillion, give or take. The number of different microscopic arrangements of that many molecules is so astronomically large that it defeats imagination, and the overwhelming, crushing, mind-boggling majority of those arrangements correspond to the equilibrium state, the state where temperature and pressure are uniform, where there are no concentration gradients, where everything is boringly, maximally spread out, the high entropy state. The probability that all the air molecules in your room would spontaneously move to one corner, leaving the rest of the room in vacuum, is not zero, but it's so close to zero that it's effectively the same thing. You could wait longer than the age of the universe, longer than trillions of ages of the universe, and it would still essentially never happen. So that's what the second law really is. At the deepest level, it's not a mystical force pushing things toward disorder. It's statistics. It's the simple, overwhelming fact that there are enormously more ways to be disordered than ordered, and random processes will naturally explore those possibilities. Entropy increases because high entropy states are vastly more probable than low entropy states. That's it. The universe isn't conspiring against you. It's just doing what's statistically overwhelming. And this insight, Boltzmann's insight, was magnificent. It explained thermodynamics from the ground up. It showed why heat flows from hot to cold, because the state where energy is evenly distributed is overwhelmingly more probable than the state where it's concentrated. It explained why gases expand to fill their containers, because the state where molecules are spread out is overwhelmingly more probable than the state where they're bunched up. It explained Carnot's limit on engine efficiency, Clausius's ever-increasing entropy, all of it from the statistics of atoms. But the scientific establishment, or at least a loud and powerful faction of it, wasn't having it. Mach publicly and repeatedly attacked Boltzmann's work. Ostwald argued that the energy-based approach, what he called energetics, made atoms unnecessary. At a famous meeting in Lübeck in 1895, Boltzmann debated Ostwald in front of a packed audience of physicists, and the debate was brutal. By most accounts, Boltzmann held his own in the argument, but the emotional toll was enormous. He felt surrounded, embattled, fighting for ideas that he was convinced were right, while the world's most prominent scientists told him he was wrong. There was also a specific, technical objection that haunted Boltzmann for years. It came from a physicist named Joseph Loschmidt, and it's actually quite clever. Loschmidt's argument went like this. The laws of mechanics are time reversible. If you filmed a bunch of billiard balls bouncing around and played the film backwards, the reversed motion would obey exactly the same laws of mechanics as the forward motion. Newton's laws don't care about the direction of time. So if the microscopic laws governing atoms are time reversible, how can you derive a macroscopic law, the second law of thermodynamics, that is not? How can time-symmetric microscopic rules produce time-asymmetric macroscopic behavior? Where does the arrow of time come from? This is actually a genuinely deep question, and Boltzmann wrestled with it. His answer was subtle. He argued that the second law is statistical, not absolute. It's not that entropy can never decrease. It's that a spontaneous decrease in entropy is so fantastically improbable that it effectively never happens for macroscopic systems. The second law is overwhelmingly likely to hold, not logically certain. In principle, a broken egg could unbreak itself. A cup of coffee could spontaneously get hotter while the air around it gets cooler. But you'd have to wait an unimaginable time for the random fluctuations to line up just right. For any practical purpose, it never happens. The second law isn't violated. It's just probabilistic rather than absolute. And for systems with the number of atoms we're dealing with, 10 to the 23rd or more, the probabilities are so lopsided that the distinction between overwhelmingly probable and certain is meaningless. This was a revolutionary way of thinking about physics. For the first time, a fundamental law of nature was being understood as a statistical tendency rather than an absolute rule. And it was right. But Boltzmann's battles took a terrible toll on him. He suffered from increasingly severe depression. He had trouble sleeping. His eyesight was failing. He felt that his life's work was being rejected. And in September 1906, while on holiday with his family in Duino, near Trieste, Ludwig Boltzmann took his own life. He was 62 years old. The tragedy is compounded by the timing. Just the year before, in 1905, a 26-year-old patent clerk named Albert Einstein had published a paper on Brownian motion, the random, jittering movement of tiny particles suspended in water, first observed by the botanist Robert Brown in 1827. Einstein showed that this jittering could be explained, quantitatively, as the result of water molecules randomly bumping into the suspended particles. And his predictions could be tested. The French physicist Jean Perrin carried out meticulous experiments that confirmed Einstein's theory precisely, and the results were so convincing that even the die-hard skeptics had to concede. Atoms were real. The debate was over. Boltzmann had been right all along. But he didn't live to see his vindication. His tombstone in the Vienna Central Cemetery bears the equation he made immortal. S equals K log W. It's one of the most profound equations in all of physics, and it stands as a quiet monument to a man who saw the truth and paid dearly for it. But let's pull back from the tragedy for a moment, because there's another figure in this story who made enormous contributions to the statistical understanding of heat and who had a very different temperament from Boltzmann. James Clerk Maxwell. Yes, the same Maxwell who unified electricity and magnetism. The same Maxwell whose equations predicted electromagnetic waves. Maxwell also did groundbreaking work on the kinetic theory of gases, years before Boltzmann extended it. In fact, it was Maxwell who first worked out, in 1860, the statistical distribution of molecular speeds in a gas, the curve showing that in any gas at a given temperature, some molecules are moving slowly, some are moving fast, and most are somewhere in between, following a specific bell-shaped distribution. Boltzmann later generalized this to include the effects of energy and derived the full Maxwell-Boltzmann distribution, which is why both their names are on it. Maxwell was also the person who invented one of the most famous thought experiments in all of thermodynamics, and it's worth telling you about because it's delightful and because it connects to ideas that would prove enormously important more than a century later. In 1867, Maxwell imagined a tiny, intelligent being. He called it a finite being, but his friend Lord Kelvin nicknamed it Maxwell's demon, and the name stuck, standing at a small door between two compartments of a gas. The gas starts at the same temperature in both compartments. The demon can see individual molecules coming toward the door, and whenever a fast-moving molecule approaches from the left, the demon opens the door and lets it through to the right. Whenever a slow-moving molecule approaches from the right, the demon lets it through to the left. Over time, the right compartment gets hotter because it's accumulating fast molecules, and the left gets cooler. Heat has flowed from cold to hot. Entropy has decreased. The second law has been violated, all without any work being done, just a tiny, intelligent being sorting molecules. Now, Maxwell didn't actually think the second law could be violated. The demon was a thought experiment designed to probe the foundations of the second law, to test whether it was truly fundamental or merely practical. And for decades, the demon caused no end of philosophical headaches. How do you exercise it? What's wrong with the argument? The answer, which took more than a century to fully work out, turns out to involve information. The demon needs to observe each molecule, determine whether it's fast or slow, and decide whether to open the door. That observation process, that gathering and processing of information, requires energy, and it generates entropy. Specifically, the demon has to store information about each molecule, and when it erases that information to make room for more, because its memory is finite, the erasure process necessarily generates heat and increases entropy. This was worked out by Leo Szilard in 1929, refined by Rolf Landauer at IBM in 1961, and fully resolved by Charles Bennett in the 1980s. And the upshot is beautiful. Information is physical. It has thermodynamic costs. Erasing a single bit of information generates a minimum amount of heat, Landauer's limit, and this minimum is enough to save the second law from the demon's mischief. Think about what that means. It means that the connection between information and thermodynamics isn't just a metaphor. It's physics. The entropy in your computer's memory chips, the heat generated when your processor erases and overwrites data, the theoretical minimum energy cost of computation. All of this is thermodynamics. The same science that was born in the coal-smeared engine rooms of industrial Britain connects, through a straight logical chain, to the theory of computing and information, Carnot and Shannon, steam engines and iPhones. That's the kind of unexpected connection that makes this subject so endlessly fascinating. But I'm getting ahead of myself. Let's come back to the 19th century for a moment, because there's one more law of thermodynamics to talk about, and it came later than the first two. This is the third law, and it concerns what happens as you approach absolute zero, that lowest possible temperature, 0 Kelvin, minus 273.15 Celsius, the point where, classically at least, all thermal motion stops, and every system settles into its lowest possible energy state. The third law was formulated by Walther Nernst, a German physical chemist, around 1906. Nernst was a fascinating character in his own right. A short, stocky, energetic man with a walrus mustache and a deep love of fast cars, which he kept crashing. He held patents on a commercially successful electric lamp, the Nernst lamp, which made him wealthy, and he used that wealth to live extravagantly. He kept a carp pond on his estate and insisted on raising the fish scientifically. He's one of those figures who seems like he should be a character in a novel. Nernst won the Nobel Prize in Chemistry in 1920 for this work, which he was characteristically pleased about. He was not a modest man. He once declared that he had found the last of the great laws of thermodynamics, and in a sense he was right. Nobody has added a fourth law in the century since, though the zeroth law got formally recognized later. His contribution to thermodynamics, which he originally called the heat theorem, and which we now call the third law, was initially stated in terms of chemical reactions at low temperatures. But in its modern, more general form, it says something elegantly simple. As the temperature of a system approaches absolute zero, its entropy approaches a minimum value. For a perfect crystal, a completely ordered, defect-free solid, that minimum entropy is zero. Perfect order. Perfect predictability. Every atom exactly where it should be, in its lowest energy state, with no randomness, and no ambiguity about the microscopic arrangement. And here's the practical consequence that matters most. The third law implies that you can never actually reach absolute zero. You can get closer and closer. Modern experiments have cooled atoms to billionths of a Kelvin, fantastically close. But reaching zero exactly would require an infinite number of cooling steps or an infinite amount of work. It's an asymptotic limit. You can approach it forever and never arrive. The universe, in a sense, keeps its last tiny bit of warmth forever out of reach. There's something almost poetic about that. The universe tends toward maximum entropy, toward the highest possible disorder, toward heat death. That's the second law. But it can never quite reach the opposite extreme either. It can never achieve perfect order, zero entropy, absolute zero temperature. It's stuck between two unreachable extremes, and everything that happens, everything that has ever happened, is the universe exploring the vast middle ground between them. Actually, before we leave the fundamental laws behind, there's one more I should mention, and its numbering is a delightful little oddity. It's called the zeroth law. Not the first, not the fourth, the zeroth. And the reason for that silly name is that it was recognized as fundamental only after the first, second, and third laws had already been numbered. It was so basic, so obvious, that nobody had bothered to state it explicitly. But when people realized it needed stating, they couldn't very well call it the fourth law, because logically, it comes before the others. So they called it the zeroth law, and the numbering went 0, 1, 2, 3, which is perhaps fitting for a science that would eventually connect deeply to the foundations of mathematics and computation. The zeroth law says this: if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. In plain language, if System A is the same temperature as System C, and System B is also the same temperature as System C, then A and B are the same temperature as each other. Which sounds so obvious it's barely worth saying, but it actually establishes something important. It establishes that temperature is a well-defined, consistent, transitive property. It's the law that makes thermometers possible. When you put a thermometer in your mouth and wait for it to reach thermal equilibrium with your body, and then you read the thermometer, you're implicitly relying on the zeroth law. The thermometer tells you about your body's temperature because it has reached the same temperature as your body, and you can trust that same temperature is a consistent, meaningful relationship. Without the zeroth law, the entire concept of temperature measurement would be on shaky logical ground. Now, let's shift gears a little. We've been in the realm of fundamental principles for a while. The three laws, the zeroth law, entropy, statistical mechanics. But thermodynamics is, at its heart, an engineering science. It was born from practical problems, and it solves practical problems. So let's talk about some of the machines and technologies that thermodynamics made possible, because this is where the abstract principles we've been discussing become things you can touch and use and benefit from every single day of your life. Let's start with refrigeration, because it's a beautiful example of the second law in action, or more precisely, in defiance. The second law says heat flows from hot to cold naturally. A refrigerator makes heat flow from cold to hot. It takes warmth out of the cold interior and dumps it into the warmer kitchen. And the second law says you can do this. You can locally reverse the natural direction of heat flow, but only if you pay a price. You have to do work. You have to put energy in. That's what the compressor in your refrigerator does. It's the engine that drives heat uphill, from cold to hot, at the cost of electrical energy. Here's how it works, roughly. Your refrigerator contains a fluid called a refrigerant. Historically, things like ammonia or freon, today usually a hydrofluorocarbon, that circulates in a closed loop. The compressor squeezes this fluid, compressing it, which heats it up. Then the hot compressed fluid flows through coils on the back or bottom of the refrigerator, those warm coils you can feel if you touch the back of your fridge, and it releases heat into the kitchen air, cooling down as it does. Then the fluid passes through an expansion valve, where it suddenly expands. And when a compressed fluid expands suddenly, its temperature drops dramatically. Now you have a very cold fluid flowing through coils inside the refrigerator, and because it's colder than the air and food inside, heat flows from the interior into the fluid. The food gets colder, the fluid gets warmer, then it flows back to the compressor, gets squeezed again, gets hot again, releases that heat into the kitchen again, and the cycle repeats, over and over. It's a heat pump. That's literally what it is. It pumps heat from where you don't want it, inside the fridge, to where you don't mind it, the kitchen. And the same principle, run in the opposite direction, gives you a heat pump for warming your house. Instead of pumping heat from inside a box to the room, you pump heat from the cold outdoors into your warm house. Same physics, same thermodynamic cycle, just pointed the other way. The history of artificial refrigeration is a great story in itself. For most of human history, keeping things cold meant harvesting ice from frozen lakes and rivers in winter and storing it in insulated ice houses. By the early 19th century, the ice trade was a serious industry. Frederick Tudor, a Boston entrepreneur, sometimes called the Ice King, built an empire, shipping ice from New England ponds to the Caribbean, to India, to anywhere hot and wealthy enough to pay for it. At its peak in the 1880s, the American ice harvesting industry employed 90,000 people and shipped millions of tons of ice per year, which is remarkable when you think about it, an entire industry built on cutting frozen water out of lakes and transporting it before it melted. But artificial refrigeration was coming. The basic principles had been understood since the 1750s, when William Cullen demonstrated that evaporating a liquid cools its surroundings, and various inventors and engineers spent decades building practical refrigeration machines. Jacob Perkins, an American inventor living in London, patented the first compression refrigeration system in 1834. James Harrison, a Scottish-born Australian, built the first practical ice-making machine in the 1850s and used it to refrigerate beer, because of course it was beer. And Carl von Linde, a German engineer, developed highly reliable ammonia compression refrigerators in the 1870s and 1880s that transformed the brewing and meatpacking industries. Before mechanical refrigeration, you could only brew beer in winter because fermentation temperatures couldn't be controlled in the summer heat. After Linde's machines, you could brew year-round. It doesn't sound revolutionary, but it changed the entire structure of the brewing industry and made possible the large-scale lager production that dominates the beer market to this day. Refrigeration also transformed the food supply. Before reliable cold chains, Fresh meat, fish, dairy, and produce could only travel short distances before spoiling. Cities depended on local farms and local slaughterhouses. The development of refrigerated railway cars in the 1870s and refrigerated ships in the 1880s made it possible to ship beef from the ranches of Argentina to the dinner tables of London, fresh fruit from California to New York, butter from New Zealand to England. The global food system you take for granted, being able to buy strawberries in December, having fresh fish in a landlocked city, keeping milk for a week instead of a day. All of that rests on the thermodynamic principles of the refrigeration cycle. Every cold chain in the world is just the second law being wrestled into submission by a compressor and a refrigerant. Now let's talk about another machine that owes its existence to thermodynamics, one that has probably shaped the modern world more than any other single invention: the internal combustion engine. We talked earlier about steam engines, external combustion engines really, because the fuel burns outside the engine and the heat is transferred to a working fluid, steam, which does the actual work. The internal combustion engine turns that idea inside out. The fuel burns directly inside the working cylinder, and the hot, expanding gases themselves push the piston. No boiler, no steam, no separate heat source. The combustion happens right where the work happens. The idea of an internal combustion engine had been floating around since the early 1800s. Various people built various experimental versions. François-Isaac de Rivaz in Switzerland, Samuel Brown in England, Nicéphore Niepce in France, who's better known for his contributions to the invention of photography. But none of these early attempts were practical or reliable. The breakthrough came from a German engineer named Nikolaus Otto, who in 1876 built the first practical four-stroke internal combustion engine, the engine cycle that still powers most cars on the road today. Here's how the Otto cycle works, and you'll see thermodynamics all through it. The piston starts at the top of the cylinder. It moves down, sucking in a mixture of air and vaporized fuel. That's the intake stroke. Then the piston moves back up, compressing that mixture into a much smaller volume, the compression stroke. This is crucial because compressing the gas heats it up, which makes the subsequent combustion more effective. At the top of the compression stroke, a spark plug ignites the compressed fuel-air mixture, and the resulting explosion, a rapid combustion that produces hot, high-pressure gas, drives the piston down with great force. That's the power stroke, the one that actually does useful work. Finally, the piston moves back up, pushing the spent exhaust gases out through the exhaust valve, the exhaust stroke. 4 strokes: intake, compression, power, exhaust. Then it repeats, hundreds or thousands of times per minute. The thermodynamics of this cycle, the Otto cycle, can be analyzed using exactly the same principles Carnot laid out. You have a hot source, the burning fuel, and a cold sink, the exhaust gases going out the tailpipe. The efficiency depends on the compression ratio, which is the ratio of the cylinder volume at the bottom of the piston stroke to the volume at the top. Higher compression ratios mean higher temperatures during combustion, which means higher efficiency, up to a point. Modern gasoline engines have compression ratios of about 10 or 11 to 1, giving them theoretical efficiencies of about 60%, though real-world efficiencies are much lower, around 25 to 35% for a typical car engine, because of friction, heat losses, incomplete combustion, and all the other messy realities that Carnot's ideal cycle doesn't account for. And then there's Rudolf Diesel. Born in Paris in 1858 to German parents, Diesel was a brilliant engineering student who became obsessed with a specific thermodynamic idea. What if you could build an engine that achieved the highest possible efficiency by compressing air to such extreme pressures that fuel injected into it would ignite spontaneously, without a spark plug. This is compression ignition, the diesel cycle, and it's fundamentally different from the Otto cycle. In a diesel engine, only air is compressed during the compression stroke, and it's compressed much more than in a gasoline engine. Compression ratios of 15 or 20 to 1. At these ratios, the air temperature rises to over 500 degrees Celsius, hot enough to ignite diesel fuel on contact. Fuel is then injected directly into this superheated air, and it burns steadily as the piston moves down. Diesel published a paper in 1893 describing his ideal engine, and after years of development, built the first working diesel engine in 1897 at the Maschinenfabrik Augsburg plant in Germany. It was heavy, it was noisy, but it was efficient. Significantly more efficient than the gasoline engines of the time, because the higher compression ratio allowed more of the fuel's energy to be converted into work and less to be wasted as heat. That efficiency advantage persists today. Diesel engines are still more fuel efficient than gasoline engines, which is why they dominate in long-haul trucking, shipping, rail, and heavy equipment, where fuel costs matter enormously. The diesel engine's impact on the modern world is hard to overstate. Right now, the vast majority of the world's goods move by diesel. The ships crossing the oceans, the trains carrying freight, the trucks on the highways. The engines in the massive container ships that carry something like 90% of global trade are gargantuan two-stroke diesel engines, some standing over 4 stories tall, producing more than 100,000 horsepower and achieving thermal efficiencies over 50%. That's extraordinary. More than half the chemical energy in the fuel becomes useful work. Carnot would have been impressed. Diesel's personal story has a mysterious ending. In September 1913, he boarded a steamship crossing the English Channel from Antwerp to Harwich. He had dinner with friends, retired to his cabin, and was never seen alive again. His body was recovered from the sea 10 days later. Whether he fell, jumped, or was pushed has been debated ever since. There were theories that he was murdered by German agents or by oil industry interests, or that he took his own life due to financial problems. The truth has never been established. But his engine lives on, and the thermodynamic principles behind it, Carnot's efficiency formula, the relationship between compression ratio and temperature, the inevitable trade-off between useful work and waste heat. Those principles are as solid today as they were when Clausius first formalized them. Let's zoom out and think about power generation more broadly, because this is where thermodynamics really runs the modern world. Right now, as you're lying there, the electricity powering whatever device you might still have on, or the electricity that cooled your room today or heated your water this morning, the overwhelming majority of that electricity was generated by a heat engine of some kind. A coal plant, a natural gas plant, a nuclear plant, these are all, at their core, heat engines. They burn fuel or harness nuclear reactions to produce heat, use that heat to make steam or hot gas, and use the steam or gas to spin a turbine connected to a generator. The details differ, but the thermodynamics is the same. Carnot's ghost is in every power plant on Earth. Nuclear power is a particularly interesting case because the heat source is nuclear fission rather than chemical combustion. When you split a heavy atom, uranium-235 usually, the fragments fly apart with enormous kinetic energy, which becomes heat when they slam into the surrounding material. That heat is used to boil water into steam, and the steam spins a turbine, just like in a coal plant. From a thermodynamic standpoint, a nuclear reactor is just a very fancy way to boil water. The nuclear physics is exotic and extraordinary. Einstein's E equals mc squared, the energy locked in the atomic nucleus, the chain reaction. But the thermodynamics of the power conversion is the same Carnot limited heat engine cycle that James Watt would have recognized. You have a hot source, a cold sink, and you extract work from the temperature difference, subject to the same fundamental efficiency limits. And the waste heat, the heat that the second law says must be rejected, goes into the cooling towers or the river or the ocean, those giant plumes of water vapor you see rising from nuclear plants, which are not smoke and not radiation, just waste heat being dumped into the environment because the second law insists on it. Even renewable energy sources brush up against thermodynamics in interesting ways. Solar photovoltaic panels aren't heat engines. They convert sunlight directly into electricity through the photoelectric effect. But there's a thermodynamic limit to their efficiency too, called the Shockley-Queisser limit, which for a single-junction silicon cell is about 33%. Wind turbines extract kinetic energy from moving air, and they're limited by the Betz limit. About 59% of the wind's kinetic energy is the maximum you can capture. These aren't Carnot limits exactly, but they're similar in spirit. Fundamental theoretical ceilings imposed by the physics of the system, not by the engineering. And here's something worth appreciating. Every time an engineer designs a more efficient engine, a better insulated building, a more effective heat exchanger, they're fighting the second law, not violating it. You can never do that, but pushing real-world performance closer to the theoretical maximum, making the most of the energy that's available before entropy claims its share. That fight has been going on for over 200 years, since Newcomen's first smoky atmospheric engine, and it continues today in the design of advanced gas turbines, supercritical steam cycles, solid-state thermoelectric devices, and a dozen other technologies that all trace their intellectual lineage back to a slim book written by a young French soldier who died in a cholera ward in Paris. There's a sort of philosophical beauty in that continuity, isn't there? The same principles Carnot articulated in 1824, the same laws Clausius formalized in the 1850s, the same statistical interpretation Boltzmann fought and died for. Those ideas are alive and working right now, in the engines and power plants and cooling systems that keep civilization running. The people who discovered these laws had no idea what the world would look like 2 centuries later, but the principles they uncovered are so fundamental, so universal, that they apply as perfectly to a modern jet engine as they did to Watt's steam engine or Newcomen's atmospheric pump. There's something else worth mentioning here, because it connects thermodynamics to another vast domain of practical importance: chemistry. Thermodynamics doesn't just tell you about engines and heat flow. It tells you which chemical reactions will happen spontaneously and which won't. It tells you whether a reaction will release energy or absorb it, and how the balance shifts with temperature and pressure. The concept of Gibbs free energy, named after the great American physicist Josiah Willard Gibbs, who spent almost his entire career at Yale, published some of the most important papers in the history of thermodynamics, and was so modest and reclusive that most European physicists didn't even know his work existed until decades later. Gibbs free energy combines enthalpy and entropy into a single quantity that tells you whether a reaction at constant temperature and pressure will proceed on its own. When chemists say a reaction is thermodynamically favorable, they mean its Gibbs free energy change is negative. That single concept underlies all of chemical engineering, drug design, materials science, and a huge swath of biology. And that universality, the breathtaking scope of thermodynamics, is something we haven't fully explored yet. Because thermodynamics doesn't just apply to engines and refrigerators and chemistry. It applies to black holes. It applies to living organisms. It applies to the flow of information. It touches the deepest questions about the nature of the universe itself. So let's go there. Let's take thermodynamics to its extremes and see what happens when you apply these 19th century ideas to the strangest objects in the cosmos. In the early 1970s, a young graduate student at Princeton named Jacob Bekenstein was thinking about black holes. Now, black holes were already well established in theoretical physics by then, solutions to Einstein's equations of general relativity that described regions of space where gravity was so intense that nothing, not even light, could escape. And the prevailing wisdom at the time, championed by some of the most brilliant physicists alive, including Stephen Hawking, was that black holes had no entropy. They were simple objects, completely described by just three numbers: their mass, their electric charge, and their spin. Everything else about whatever had fallen into them was lost. A black hole made from the collapse of a star, and a black hole made from the collapse of an enormous pile of encyclopedias would be identical, as long as the mass, charge, and spin were the same. All the information about what went in was erased. But Bekenstein saw a problem. If you throw a hot cup of coffee into a black hole, the coffee had entropy, a lot of it. And after the coffee crosses the event horizon, that entropy seems to vanish from the observable universe, which means the total entropy of the observable universe just decreased. And that violates the second law. The second law says entropy always increases, or at best stays the same. It doesn't decrease. Not ever. So either the second law breaks down when black holes are involved, or the black hole somehow has entropy of its own, entropy that increases when things fall into it. Bekenstein proposed that black holes do have entropy, and that it's proportional to the area of the event horizon, the boundary of no return, the surface of the black hole. As stuff falls in and the black hole grows, its horizon area increases, and its entropy increases. The second law survives. Hawking initially resisted this idea. If a black hole has entropy, then by the same thermodynamic reasoning, it should have a temperature, and if it has a temperature, it should radiate energy. Like any warm object, it should glow. But nothing can escape a black hole. That's the whole point. So a black hole can't radiate. Therefore, it can't have a temperature. Therefore, it can't have entropy. Bekenstein must be wrong. But then Hawking did the calculation. He applied quantum mechanics to the vicinity of a black hole's event horizon, and he found something that astonished him and astonished everyone else. Black holes do radiate. They emit a faint thermal glow of particles, now called Hawking radiation, produced by quantum effects near the event horizon. The temperature of this radiation is inversely proportional to the mass of the black hole. Small black holes are hotter than large ones, and the temperature is consistent with the entropy that Bekenstein had proposed. The whole package fit together perfectly. Black holes are thermodynamic objects. They have temperature, they have entropy, they obey the laws of thermodynamics, and over astronomically long timescales, they will slowly evaporate, radiating away their mass as Hawking radiation, until eventually, after an almost unimaginable span of time, something like 10 to the 67th power years, for a black hole the mass of our sun, they disappear entirely. Think about what just happened there. Thermodynamics, a science invented to understand steam engines, turned out to apply to the most extreme objects in the universe. The same second law that Clausius formulated to explain why heat flows from hot to cold. The same entropy that Boltzmann connected to the statistics of atoms. Those ideas reached all the way to the event horizons of black holes and told us something profound about the nature of gravity, quantum mechanics, and the structure of space-time itself. If that doesn't give you a sense of how fundamental these laws are, I don't know what will. And there's a thread here that connects to something even deeper, the relationship between entropy and information. Remember Maxwell's demon? the little thought experiment where an intelligent being sorts fast and slow molecules to decrease entropy? We mentioned that the resolution involves information. The daemon needs to store and eventually erase information, and the erasure generates entropy. Well, the black hole information problem is a version of the same puzzle, writ large. When things fall into a black hole, is the information about what they were, their structure, their identity, the arrangement of their atoms, truly lost? Or is it somehow preserved, encoded in the Hawking radiation that the black hole eventually emits? This question, first posed clearly in the 1970s, has been one of the deepest and most contentious puzzles in theoretical physics for half a century. Hawking initially argued that the information was destroyed, which would violate a fundamental principle of quantum mechanics called unitarity. Most other physicists disagreed, and Hawking eventually conceded in 2004 that information is probably preserved after all. But exactly how it's preserved, how the information gets out of the black hole, is still an active area of research. String theory, holographic principles, quantum error correction, some of the most advanced ideas in modern theoretical physics are focused on this problem. And it's all, at bottom, thermodynamics, entropy and information, two concepts that turned out to be intimately, mathematically, physically linked. Let's come back down to earth a little, literally, and talk about something closer to home, thermodynamics in living systems. Because you, lying there, breathing, metabolizing, thinking, you are a thermodynamic system. And a very interesting one. Living organisms are sometimes described as low-entropy islands in a sea of increasing entropy. And that's true, up to a point. Your body is extraordinarily organized. Trillions of cells, each one a complex factory of proteins and enzymes and membranes, each performing specific functions with remarkable precision. That kind of order is low entropy, and you maintain that order. You fight the relentless trend toward disorder by consuming energy. You eat food, which is a concentrated source of chemical energy, stored in the chemical bonds of sugars and fats and proteins. You break those bonds through metabolism, extract the energy, and use it to build and repair and move and think. And the waste products, carbon dioxide, water, heat, are higher entropy than the food you started with. So you survive by exporting entropy. You take in low entropy matter, food, and expel high entropy matter, waste heat and exhaled gases. And the net effect is that you decrease entropy locally, inside your body, while increasing it globally, in your surroundings, by an even larger amount. The total entropy of the universe goes up, as the second law demands. You're not violating thermodynamics, you're surfing it. This perspective, understanding life as a thermodynamic process, was developed most profoundly by the physicist Erwin Schrödinger. Yes, the same Schrödinger of quantum mechanics fame and the famous cat thought experiment. In 1944, Schrödinger published a small, influential book called What is Life?, in which he argued that living organisms maintain their organization by feeding on what he poetically called negative entropy, or negentropy, as some later writers put it. He meant that organisms consume order from their environment, the structured chemical energy in food, and use it to maintain their internal order, excreting disorder as waste heat. Schrödinger's book had an enormous influence on the generation of scientists who went on to discover the structure of DNA and launch the field of molecular biology. James Watson, Francis Crick, and many others have cited it as a key inspiration, and the thermodynamic perspective it championed, that life is fundamentally about managing entropy, about using energy flows to maintain complex organization, is now central to our understanding of biology. There's another branch of thermodynamics that's particularly relevant to living systems, and it's called non-equilibrium thermodynamics. See, classical thermodynamics, the thermodynamics of Clausius and Kelvin and Boltzmann, is really about equilibrium. It describes systems that have settled into their final state, where nothing is changing, where all the temperatures have equalized and all the pressures have balanced out. But most of the interesting things in the world, life, weather, ocean currents, the formation of stars and galaxies, happen far from equilibrium. They happen in systems where energy is flowing through, driving processes, creating structures. The study of non-equilibrium thermodynamics was pioneered by a Belgian physical chemist named Ilya Prigogine, who won the Nobel Prize in Chemistry in 1977 for his work. Prigogine showed that systems far from equilibrium can spontaneously develop complex, organized structures, what he called dissipative structures, that are maintained by the continuous flow of energy through the system. Think about a whirlpool forming when you drain a bathtub. The water spontaneously organizes into a structured, swirling pattern, and this pattern persists as long as water keeps flowing through. Or think about the convection cells that form in a pot of water heated from below. Regular, hexagonal patterns of rising and sinking fluid that emerge spontaneously when the temperature difference is large enough. These are ordered structures, created and sustained by energy flow, not despite entropy, but because of it. The flowing energy drives the system far from equilibrium, and new kinds of order emerge. Prigogine argued that life itself might be understood as a dissipative structure, a spectacularly complex one, maintained by the continuous flow of energy from the sun through the biosphere, and ultimately radiated back into space as waste heat. Life doesn't violate the second law. It exploits it. It channels energy flows into the creation and maintenance of biological complexity, while increasing the total entropy of the universe in the process. This is one of those ideas that, once you see it, changes how you look at everything. The city you live in, the economy you participate in, the biosphere that sustains you. All of these are dissipative structures. All of them are maintained by flows of energy. All of them are exporting entropy to their surroundings. All of them will collapse if the energy flow stops. Your body maintains its temperature, its pH, its chemical balance, by continuously processing energy and exporting waste. When that stops, when the energy flow ceases, you stop. That's what death is, thermodynamically. The end of the energy flow that maintains the dissipative structure, and the system relaxes toward equilibrium, which is another way of saying that entropy wins in the end, as it always does. But let's not dwell on that. Let's think instead about the future, and about the enormous practical challenge that thermodynamics places at the center of modern life, the energy problem. Here's the situation. Human civilization runs on energy, enormous amounts of it. We use it to heat our homes, cool our food, power our factories, move our vehicles, run our computers, light our cities. And most of that energy, still, even now, in the 21st century, comes from burning fossil fuels. Coal, oil, natural gas. These are concentrated stores of chemical energy, the compressed and transformed remains of ancient organisms, formed over hundreds of millions of years. We're burning through them in centuries, and when we burn them, two things happen. First, we release carbon dioxide into the atmosphere, which is changing the climate in ways that are already causing significant problems and will cause much more. And second, and this is the thermodynamic point, we release heat. Every engine, every furnace, every power plant produces waste heat, as the second law demands. The entire energy infrastructure of civilization is, from a thermodynamic perspective, a massive machine for converting concentrated chemical energy into useful work and then into dispersed waste heat that radiates into space. The challenge of the 21st century, one of them at least, is to find ways to power civilization that don't depend on burning ancient carbon. Solar, wind, nuclear, geothermal, hydroelectric. These are all ways of tapping into energy flows that don't involve fossil fuels. Solar panels capture energy from sunlight. Wind turbines capture energy from the movement of air, which is itself driven by solar heating of the atmosphere. Nuclear plants tap into the energy stored in atomic nuclei. Geothermal systems use the heat flowing from the Earth's interior, and all of them, every single one, operate within the constraints of thermodynamics. The efficiency limits are there, the waste heat is there, the entropy increase is there. You can be clever about how you use energy, more efficient engines, better insulation, waste heat recovery, combined heat and power, but you can't escape the fundamental laws. And that's okay. The laws aren't your enemy. They're the rules of the game, and understanding them is what lets you play the game as well as possible. Every improvement in engine efficiency, every advance in solar cell technology, every better designed heat exchanger, these are all victories won by understanding thermodynamics more deeply and applying it more skillfully. The engineer who designs a combined cycle gas turbine that converts 60% of the fuel's energy into electricity, compared to the 1% that Newcomen's engine managed 300 years ago, that engineer is standing on the shoulders of Carnot and Clausius and Boltzmann and Joule and Watt and every other person in this story. The science they built is the science that makes it possible. There's one more grand theme I want to touch on before we let this all settle. And it's the biggest one of all, the ultimate fate of the universe, as thermodynamics describes it. We've mentioned it in passing, the heat death, but it deserves a few more moments of your attention because it's one of the most remarkable predictions in all of science. The second law says that the entropy of the universe tends toward a maximum. Energy becomes more and more evenly distributed. Temperature differences smooth out. Usable energy, energy capable of doing work, gradually becomes unusable. Stars burn through their nuclear fuel, galaxies fade, black holes evaporate, and eventually, after spans of time so vast that they make the current age of the universe look like the blink of an eye, the universe reaches thermodynamic equilibrium, maximum entropy, no temperature gradients, no energy available to do work, no structures, no complexity, no life. Just a thin, cold, uniform soup of particles and radiation, slowly cooling toward absolute zero without ever reaching it. The ultimate victory of the second law, the final state. Now, this isn't going to happen anytime soon. The universe is about 13.8 billion years old, and it's still very far from thermodynamic equilibrium. Stars are still forming, galaxies are still colliding, planets are still orbiting, life is still flourishing, at least on this one small rock. The timescales for heat death are so enormous that they're measured in powers of 10 to the 100th years, or more, depending on which processes you're tracking. For all practical purposes, the universe has barely begun, but the direction is set. The arrow of time points in one direction, and that direction is the direction of increasing entropy. Every tick of every clock, every heartbeat, every thought in your head, every breath you take, these are all irreversible processes that increase entropy and push the universe, infinitesimally, toward its final equilibrium. You are part of that arrow. Your life is a tiny, beautiful, improbable eddy in the great river of entropy. a momentary swirl of complexity and order, sustained by energy flowing from the sun, destined eventually to dissolve back into the background. And there's something strangely peaceful about that, isn't there? Not depressing, peaceful. Because it means that the very fact of your existence, the fact that there's a you lying here right now, capable of thinking about these things, is thermodynamically extraordinary. You are an astonishingly unlikely arrangement of atoms, held together by energy flows and chemical bonds, and the remarkable self-organizing properties of matter, far from equilibrium. Every second you exist is a small miracle of thermodynamics. And the science that explains all of this, the science we've been tracing tonight, from the ancient mystery of fire to the boring of cannon barrels in Munich, from Newcomen's smoky pump to Watt's Sunday walk across Glasgow Green, from Carnot's slim book that almost nobody read to Joule's meticulous paddle wheel experiments in a Manchester brewery, from Clausius inventing the word entropy to Boltzmann carving it into the foundations of statistical physics, from the refrigerators keeping your food fresh to the power plants lighting your city, to the black holes swallowing light at the centers of distant galaxies. This science is one of the great achievements of the human mind. It tells us something profound about the nature of reality. Energy is conserved. Entropy increases. You can't reach absolute zero. 3 laws, essentially. And from those 3 laws, an entire universe of consequences flows. There's a story, probably apocryphal but too good not to mention, about the physicist C.P. Snow, who in 1959 gave a famous lecture about the divide between scientific and literary cultures. He argued that educated people should know the second law of thermodynamics the way they know the works of Shakespeare, that it's a fundamental part of human knowledge. And he was right. The second law isn't just a piece of physics. It's a statement about the nature of time, the nature of order, the nature of life, and its ultimate limits. It's one of the deepest truths we've ever found. So as you're lying there, feeling your body radiate its 100 watts of warmth into the surrounding air, feeling the blankets slow the escape of that heat, feeling your breath carry warm, moist, high-entropy air out of your lungs and into the room, know that you are participating in the great thermodynamic drama of the universe. Every exhale increases the entropy of the universe by a tiny amount. Every heartbeat converts a little bit of the chemical energy stored in your body into kinetic energy and heat. You are a dissipative structure, a far from equilibrium system of extraordinary complexity, maintained by the steady flow of energy that started in the nuclear furnace of the sun, traveled 93 million miles as light, was captured by plants and converted into chemical bonds, was eaten and digested and metabolized, and is now keeping you warm and alive and conscious, at least for the moment. And if consciousness is fading, if your thoughts are starting to soften around the edges, and the ideas are beginning to blur together pleasantly, that's fine. That's good. Your brain is easing off the throttle, reducing its metabolic rate, letting the neural activity settle into the quieter patterns of sleep. Even that transition is thermodynamics. The waking brain consumes more energy and generates more entropy than the sleeping brain. Sleep is, in a small way, a nightly retreat from the thermodynamic intensity of consciousness. Your body is still running, still maintaining its temperature, still breathing, still circulating blood. The dissipative structure doesn't shut down in sleep, but it throttles back, conserves energy, repairs and rebuilds in the quiet of reduced activity. The laws of thermodynamics will be here tomorrow when you wake up. They'll be in the hot water coming out of your shower, heat flowing from the water heater through the pipes and into the cooler water, exactly as Clausius described. They'll be in the steam rising from your morning coffee, a phase transition from liquid to gas, driven by the thermal energy of the hot water. They'll be in your car engine, if you drive, a 4-stroke Otto cycle, converting chemical energy into motion and waste heat, limited by Carnot's efficiency. They'll be in the power grid that charges your phone, heat engines spinning generators, electrons flowing through wires, energy cascading through the system with losses at every step, entropy increasing all the while. These laws are woven into the fabric of everything. They're as inescapable as gravity, as reliable as the sunrise, as universal as mathematics. And they were discovered by human beings, curious, stubborn, brilliant, sometimes tragic human beings who looked at fire and engines and ice and asked, "What are the rules? What's really going on here?" And slowly, painfully, beautifully, over 2 centuries, they found out. That's thermodynamics, the science of heat and energy, and the arrow of time, the science that says, you can't win, you can't break even, and you can't quit the game. But the game itself, the endless dance of energy flowing, entropy increasing, structures forming and dissolving in the great stream, the game is magnificent, and you're in it, right now, breathing, warm, alive. So let that be enough for tonight. Let the ideas settle. Let the warmth of the blankets do what the second law says they do. Slow the flow of your heat into the cooler air, keep you comfortable, keep you warm. And let the same thermodynamic processes that power the stars and drive the oceans and sustain every living thing on this planet carry you, gently, into sleep.